This is lesson 22 on truth trees for consistency. Now that you're comfortable with truth tables, formal proofs, and truth functional completeness, we're moving into a new unit of intermediate logic on truth trees. We're going to start with truth trees for consistency. Remember what consistency means. It means a set of propositions is consistent if the set of the propositions can all be true at the same time. We've used truth tables, especially shorter truth tables, as a helpful method of determining the consistency of propositions. This, of course, gives you a clue that truth trees are going to do the same sorts of things that truth tables do. You can use truth trees to determine consistency, equivalence, and validity as well. It's just going to approach the task in a slightly different way. Truth tables sort of look at patterns to see that propositions are consistent, equivalent, or arguments are valid or invalid, whereas truth trees, what we're learning about now, show where consistencies or where contradictions appear in a more visual way, but they don't add any new abilities as far as being able to determine relationships between statements or validity of arguments. But the visual nature of a truth tree is sometimes more helpful to students. Truth trees are a visual method, like I said, of breaking down compound propositions into their components. This also allows us to determine the consistency of a set of propositions by showing where any contradictions occur among those components. You'll see how this is more visual than truth tables, but first you need to learn a few new terms to help you understand the basics of truth trees. First new term, the components of compound propositions are called literals. So what a truth tree does is it takes a set of propositions, breaks them down into their components called literals, and looks for where those literals contradict. A literal is a simple proposition as a variable, lowercase p or q, or constant, uppercase a or m or b or whatever, or its negation, a or not a, p or not p, those are literals. Now, the second term you need to know is decomposition. A truth tree shows the decomposition of compound propositions into literals. We decompose a compound proposition into its literals. So let's take a look at a very basic example of using a truth tree to test for consistency. Consider this set A, not B, and C. We have two propositions. A is a simple proposition, and not B and C is a compound proposition. We're asking the question, what would be the truth values of each of the constants if these propositions were both true? So for A to be true and for not B and C to be true, what would the truth values of A, B, and C have to be? Well, obviously for A to be true, A would have to be true. For not B and C to be true, not B would have to be true, and C would also have to be true. And so we decompose, which means split or break down the compound proposition into two parts, not B and C, one right above the other. Once we've decomposed the proposition, we check it off with a check mark. So we've basically replaced the compound proposition not B and C with the literals not B and C. That's why we check it off. We know we can forget about it. Now we ask ourselves, what are the truth values required for A, not B, and C to be true? For A to be true, A would have to be true. For not B to be true, B would have to be false, right? Because it's negated. And then for C to be true, C would have to be true. So we've decomposed the two propositions, A and not B and C, into their literals, A, not B, and C, and we've recovered, that's another word to keep track of, the truth values. We found the truth values of the individual constants that would be necessary for both of those propositions to be true at the same time. As with formal proofs, it's customary to number and justify each step in a truth tree. So we've seen how to decompose that basic proposition, but let's look at what the actual truth tree would look like. It would look something like this. I'm going to work through this set again. So the first step would be A, and we label it SM. SM stands for set member. That's our first set member in our set of propositions. Then number 2, SM again, not B and C. That would be our second set member. So now what we do is we decompose not B and C into not B and then C right below it, and then we justify that with 2 conjunction decomposition. Now, so from step 2, not B and C, we've decomposed that compound proposition into its literals, not B and then C, and the rule we used was step 2, conjunction decomposition, abbreviated 2.D. Once you've decomposed a proposition completely, you check the proposition off in step 2. Now we've decomposed each proposition into its literals, A, not B, and C. Those are all the literals, and there's no contradiction. So what we do is we put a circle underneath that and call it an open branch. An open branch in the truth tree is where there's no contradictions along an entirely decomposed truth tree. And when you have an open branch, that means the propositions are consistent and you can recover the truth values. A is true. For not B to be true means that B is false and C is true. That's a very basic truth tree, but that's what it looks like. Numbered steps, justified steps, checked off, decomposed propositions, consistent or inconsistent, open branches, and if the set of propositions is consistent, we recover the truth values of the constants or variables. Okay, you're going to see several examples so that we understand how this works. We need to look at this set. D and not E, not E. We're going to learn another decomposition rule here. So our first set member is D and not E. Our second set member is not E. Now we can decompose the not E into E. Our justification for that is double negation decomposition. So we actually lose the negation symbols, and that comes from step 2. And then, once that's completely decomposed, we check it off back in step 2 as part of the set member. Now we need to decompose the compound proposition D and not E. It decomposes into D and not E, and we justify each step as step 1 conjunction decomposition, or step 1.D. Now we see a contradiction between E and not E, line numbers 3 and 5, and so we label that branch as 3x5, which means the proposition in line 3 contradicts the proposition in line 5, and that means that's a closed branch, in contradiction to the open branch we saw earlier. Furthermore, because this is the only branch in the truth tree, this is an inconsistent set. It's impossible to recover the truth values. There's no way for those two propositions to be true at the same time. Remember, that's what we're checking for here for consistency. Another one. Consider this set, F or G, not F, so that you can see how to decompose disjunctions. So set member number 1 is F or G, set member number 2 is not F. Not F is already a literal, it's a negation of a simple proposition, but F or G is a compound proposition that we need to break down into its literals. In truth trees, disjunctions break down this way. They branch. That's because for the compound proposition F or G to be true, either F would have to be true or G would have to be true. So this is a disjunction decomposition from line 1. Of course, we check off that initial proposition once it's properly decomposed. And now we have two different branches that we have to look at to determine the truth value of what would make all these propositions consistent. First of all, we see that lines 2 and 3 contradict along this branch. F contradicts with not F, and so we write 2x3. But along this other branch, there is no contradiction. It's an open branch, and so we label it O, and we have a consistent set. Right, consistent, because we have an open branch and everything along that branch is entirely decomposed into literals. Along that open branch, not F, G are our two literals. F or G is checked off, we can ignore it. If it's consistent, and it is, we can recover our truth values for the two constants here. For not F to be true, F would have to be false. For G to be true, G would be true, and we've recovered those truth values. So we have a completed truth tree again. The compound propositions have been broken down into literals on different branches. There's a closed branch and an open branch. You only need one open branch to have a consistent set because we've shown that it's possible along that open branch for the statements in our original set to be true at the same time. And that's what we mean by consistency. I'm guessing your head is still spinning a bit, so let's spin faster. You can keep up. Let's take a look at P and not Q and not P or Q. We label number 1 as our first set member, and our second set member is, of course, not P or Q. Now let's decompose proposition 1. It decomposes into P and not Q. We justify each step with a 1 conjunction decomposition, 1 being the line number we were decomposing, and conjunction decomposition, the dot D, being the rule we were using. Like so. And now we've checked off that P and not Q because we've decomposed it completely into literals. Next, we decompose proposition 2. It's the only proposition along this branch that is not a literal, and so that branches into two different branches, not P on one side, Q on the other. We justify that as 2 disjunction decomposition, and then we check it off because we've decomposed it, like so. Now, along these branches, All we have left is literals and checked off compound propositions. And so we have decomposed the propositions, and now we can analyze the truth tree. Here we see that there's a contradiction. The literal in line 3 contradicts the literal in line 5. 3 contradicts 5. And along this branch, we see the same sort of thing. The literal in line 4 contradicts the literal in line 5. So this is an inconsistent set. We're done, and you can write inconsistent. We have a closed truth tree. There are no open branches. And in a closed truth tree, where every branch has a contradiction, then it's an inconsistent set. Those two statements, in fact, contradict each other. So how about these? There's one more thing we're going to learn from decomposing the truth tree for this set of propositions. So the first one is P and Q. Second is Q or not R. Those are our set members. We're going to decompose one by putting one right above the other, justified by conjunction decomposition. P and then Q. And check off one because we've decomposed it. Now we branch the Q or not R with a disjunction decomposition and check that off. Now we have two branches to consider, and with both branches, everything's either broken down into its literals or it's checked off. We've entirely decomposed the propositions in our set. Good for us. Now we can analyze them in order to see whether they're open or closed. There are no contradictions on either branch. PQ here, PQ not R, no contradictions. So we have two open branches, and we can recognize that it's a consistent set and recover the truth values. Our three constants, like I said, are P, Q, and R. Along this branch, the right one, P is true, Q is true, R is false. But look at the left branch. Along that branch, we only have P and Q. R doesn't appear. That means R can have any truth value, and it doesn't matter. Now we've already looked at P and Q being true and R being false, and so it's possible for P and Q to be true and R true, because R does not appear on that branch, and so R can be false or true, it doesn't matter. And so what we're saying is this: if we give the original sets those truth values we just talked about, both of the propositions in the set will be true. In other words, if P is true, Q is true, and R is false, P and Q is true because we have true and true. Q or not R is true because we have true or not false, and true or not false is true. But if we give them all the value of true, then true and true is true, and true or not true is also true. So if we substitute those truth values into those propositions, we find out they're both true. That's what a truth tree does for us. It allows us to recover the truth values by which the propositions in the set can all be true. To bring things full circle and compare to truth tables, basically when we recover the values in a truth tree, the values we recovered would match the values of the variables in the rows in a longer truth table where the original set members were true. Try the longer truth table yourself now if you'd like. You'll get the same values. So to summarize, here's the method for truth trees for consistency. First, write down the set members on numbered lines, labeling them SM for set member. Continue to number each step as you decompose the compound propositions into literals. A literal is either a variable or a negation of a variable, or a constant or the negation of a constant. Justify each step by stating the line number of the proposition along with the decomposition rule used. The rules we learned today are double negation decomposition, conjunction decomposition, disjunction decomposition. You check off each proposition as it is decomposed, and from then on, you ignore that proposition and you look at just the literals. When the set has been entirely decomposed, examine each branch for contradictions. Branches which show no contradictions are open branches and are marked with a circle. Branches with a contradiction are closed branches and are marked with an X between the step numbers which show the contradiction. If there is at least one open branch, the set is consistent and the truth values which show consistency may be recovered. See? Not so hard. You've mastered truth tables and formal proofs. A truth tree can't faze you. Now you get to go on to exercise 22, where I ask you to use the method of truth trees to determine the consistency of the following sets of propositions. And of course, recover the truth values for all consistent sets. So make sure you number each of the steps, you label them SM, you decompose those propositions which are not already literals. In number 1, for example, P is already a literal, so you just have to decompose not Q and R. Make sure you check off every proposition that you decompose, and from then on, ignore it. And make sure you identify whether along a particular branch there's a contradiction or not. If there is a contradiction, you use the line numbers which show the contradiction. If there's no contradiction along an entirely decomposed branch, you put a circle on the bottom and you recover the truth values. I joke about it, but you really aren't going to have trouble doing these. On the wall behind me, you can see the 50 adorable fallacies from the amazing Dr. Ransom's Bestiary of Adorable Fallacies. This is the informal fallacy book that all of your family is going to love reading together. Second book I wanted to show you is a book written just for classical homeschoolers, Classical Me, Classical Thee, Squander Not Thine Education. This book explains why you have to do all the classes you're trying to do. So please remember to subscribe and hit the bell. You can check the links below in the description for these two books and anything else from Logos Press. Thanks for watching.